Cool. Okay, so for my extra credit problems on chapter 1, I chose number 11, just trying to verify which of the following satisfies or is a solution to this differential equation. And just like looking at what's given right off the bat, I know that I want this to equal 0 and this to equal 2. Um, I can't really like say more than it just seemed really obvious. I mean, um, so, but let's just, for hypothetical sake, like maybe there's another answer that I'm not seeing. Um, let's try, well, y equals 0. That could work, but no, it can't because 9 times 0 is just 0. So, and the second derivative of 0 is still 0, so that's not going to do me any good. What about 2x? I mean, this is just to verify, just to make sure like I'm not missing something. Well, the first derivative of that is just going to be, using the chain rule, obviously it's just going to be 2, right? Um, and that's that's cool. Um, and then so that is helpful, but it's to the second derivative. So the second derivative of 2x is 0. Oh, okay. I don't know what that's about. And if you plug in just y straight up into of y equals 2x into that 9, you're gonna get 18. X equals 18. So we don't want that either. So the only, and then moving forward, obviously the first derivative of this um, is just going to be 4x, and then the second derivative is just going to be 4. So none of these really work except for y equals 2. So the second derivative of 2 is just 0 plus 9 times 2 equals 18 indeed. So that felt good. They're never that easy. But there's that. Moving on, I did number 4 on chapter 2. I wanted to see if this was separable. The reason I did is because we've been working a lot to identify if things are linear or not. But we haven't really thought much about, or at least I haven't really thought much about separable versus not separable. And so this right here just looks like a form 6 kind of problem where you have this, or, you know, right before the form 6 where you have this in front of the derivative of something, and then you got the a naught xy equals 0. So like this looks like something where we would use the integrating factor situation, but there's no g of x over here. It's just a 0. So I thought, why not just try and mess with the variables a little bit? Um, and so what I did was I just moved things over. We just separated out this term, and it's just negative. You keep everything with it. Oh, this is a definition. Obviously, the derivative of y is just the same as the change in y over the change in x over some like tiny increments, right? So I just had to write that out. And so this is, this term, I'm left with this term. But then I was able to just divide this by this term, which is what we see over here. And finally, I'm left with this kind of annoying y, and the dx is still over here, so I don't have my variables together. I want my y's with my dy's. So I just multiplied this side by dx, multiplied that side by dx, divide, just did the inverse of what needed to be done. So I get dy over y equals this term over this term dx, and that's separable to me. That seems like we got our x's and our dx's on this side. This is like some kind of coefficient term or whatever. And then that's just, y to the -1 over here, so we can eventually integrate that and do what we need to do if we need to. So that made sense to me. It was a little tricky. It was more like theoretical than anything, but it worked out. Okay, then number 23, it was just solving this differential equation. And so the first thing I did when I saw this was, okay, I identified that we have our deriv right here. We have this, and if you know, this is the dependent variable, right? Like, let's say it's y, like, because we're used to seeing it in that term, like, so let's say that's like dy, and then we will have over here y. Okay, well, we can get it into form 6, and it looks very familiar. So that's why I said step 1, rewrite to get into form 6, and that's exactly what I did. I just divided this side by t, this side by t, got dq over, I got the derivative of q over t, plus q over t equals, one of the t's canceled out nicely. Okay, cool. Just continuing on with what we know from the integrating factor theorem, or the integrating factor. I know that this right here, because this is the same as just 1 over t, right? That this is the coefficient, the leading coefficient. So that's that p of x term that we use when we take e to the p of x dx. And so obviously there's no x's in this, so it's just 1 over t, with respect to t, which gives us this nice e to the ln of t. That obviously is going to go away, and t is our mu of x. Okay, great. Making sure that we did this right, we multiplied both sides of the equation by that mu of x. And just to verify, this mu of x right here is the same as that x term with y, right? So there's that, so that's good. And so we get this product rule, essentially. We get, we can call this f, and this is its respective derivative, right? And then we have a derivative right here, and its inverse is going to be this q. So we know that we're on the right track. We take the integral of, and once we see this, we're able to kind of factor things around a little bit, and we take the integral of this mu x value times our y with respect to the independent variable. Do the same on the other side, and then we remember that it's an integration by parts. That's the only slowdown in this problem, so we just got to choose the appropriate u, du's, v's, and dv's. And just remembering back from good old Calc 2 days, which for me was a very, very, very long time ago, but that's okay. We know that it's the same as just when it's, it's in one term times another. We know that it's just uv minus the integral v du. We set that up, plugged away, chugged away, made sure everything was cool, and this is the final solution. It took a little while only in the Calc 2 part, but everything else made perfect sense. Feeling really comfortable with doing that 2.3 section stuff. So yeah, let me know if you have any questions, if you liked any of this, or yeah. Okay, thanks.